Okay, so let's start. Today we're going to talk about one of the most fundamental and easiest problems in algorithms, which is just sorting. So hopefully a very easy session, this one. So sorting is a very simple problem. In the input, I'm just going to give you a bunch of items. Now for this session, just imagine that the items are some numbers, some integers that you can have an order on. But in general, what I really care about is that I can compare my items. So for any two items, I can say which one is smaller, which one is larger. And this comparison can be based on anything. But for now, let's say that my input is just n items. And I'm going to call them A1, A2 to AN. And let's assume that the items are also distinct, so we don't have any ties when we want to compare them between any two items. One of them is smaller, one of them is larger. Of course, all of our algorithms also work if we have ties. That's not a big deal. And then in the output, you should basically just sort these items. So you should output a permutation of the original items. So permutation AI1, AI2 to AIN of the items. And of course, I want them to be in sorted order. So I want this one to be the smallest element. I put the smallest element first. You can also put the largest element first, your choice, and so on. So I want them to be in a sorted order. Okay. So today we're going to just see several algorithms to achieve this. Actually, in the next session, we're going to talk about heaps and more complicated algorithms for the same problem. And then at some point, we will prove that one of the algorithms that we see today, which is merge sort, is actually optimal in terms of the number of comparisons that it performs. But let's not get ahead of ourselves. Let's just talk about how to do the sorting. So the first thing I have to ask is, how is my input given to me? Or if I just read the input from a file, how am I going to save it in my program? Now, generally speaking, we want to think about two different data structures here. I can either save it as an array or as a linked list. These are the two that we will consider. Of course, you can save it in many other ways as well. So I assume you already know what linked lists are, and I assume you can implement them. If not, I've put some videos on Canvas. Please watch those. And by the way, this is going to happen all the time. I'm going to just give you a bunch of videos to watch. For every lecture, you will probably have to watch like 5 lectures online. Now, but the online lectures are not 1 hour and a half, they're 10 minutes each. So let's talk about this. So here's the thing. Let's come up with the simplest idea that we can think of. And actually, I brought some cards because we want to do sorting, so let me see. Okay. Does this work? Yes, you can see. Okay, unfortunately, I don't have playing cards, but I have a bunch of cards that the university gave me, but I don't use them, so I can just use these cards here for sorting. So let's say I have a bunch of cards with a bunch of numbers on them, and I want to sort this. These are too many. Let's ignore some of them. Oh. Why is it like that? This is the video that I'm sharing, right? Oh, okay. It's this one. Okay. Now, hopefully, it will work. And I hope that it's also being recorded. I'm not sure. Okay. Anyway, I don't have playing cards. Sorry. So these are a bunch of cards, and I want to sort them based on the number. Now, here's the first thing that comes to my mind. I can always find the card with the smallest number and put it first, right? So I can just go over all of my cards, and here I see that 2 has the smallest number. So I just take out 2. Okay. And then I do the same thing again. Now the next smallest number, again, every time that I want to find the smallest number, unfortunately, I have to go over my cards. So I go over all of my cards. I see that 6 is the next one. I put it there. Now, again, I go over my cards. 7 is the next smallest one. I go over the cards. 8 is the smallest one. And then 9, 10, and 11. Okay, so this is what I'm doing. Every time I'm just finding the smallest possible card and putting it first. Right? Now, imagine if I wanted to implement this with arrays. That would be super easy, right? I have an original array, which were the cards that were unsorted. And every time I find the minimum element and I put it in a sorted array, right? And I can keep doing this. So this is our first algorithm. I can also do kind of a different algorithm. I'm not really great at shuffling cards, so give me some time. A little bit. Okay. So I believe this will do. Not a great shuffle. Okay. Let's say these are my numbers now, 5, 4, 7, 3, 2, 6. Now, previously, what I did was every time I found the minimum element, instead of that, I can just take the first element every time, but insert it in the correct place. So I take 5. Initially, my sorted array is empty, so I just put it there. Then I take 4, and I realize that I have to put it before 5. Right? Then I take 7, I compare it with 4 and 5, and I see that I have to put it after 5. Then I take 3, I compare it with 4, I see that it should go before 4. Then I take 2, I compare it with 3, it has to just go there. Finally, I take 6, I compare it with them, and I see that it has to go. Okay. So this is my second algorithm. The first algorithm is usually called selection sort. The second one is called insertion sort. Honestly, both of them are really simple algorithms. I don't care if you remember the names as long as you can code them. Okay. But now the thing that we have to really talk about is the data structure that we're using, because of course in the computer we're not using cards, we're using either an array or a linked list. Now, here's the thing. Let's say I have this list, and let's say I want to insert 4 into it. So 2 questions. First of all, how much time do I need to figure out where to insert 4? And remember, this is sorted already. So if this sorted list is actually an array, I can do a binary search, and in logarithmic time, I can know where I have to insert my number 4. But then the problem is, since it's an array, I cannot just put it in between. I have to actually shift everything to the right so that I create space for this 4. Right? So in an array, if it's sorted, searching takes logarithmic time, but insertion in the worst case takes linear time because I might have to shift everything forward. Like the worst case is that I have to insert at the beginning of my array and I have to shift it. Now, on the other hand, if this is a linked list, that means I don't have an overview like this. I just know maybe my first element or my last element. And from every element, I can go to the previous one or to the next one. So I cannot do binary search. All I can do is I can keep walking on my linked list, maybe from the beginning to the end or the end to the beginning, depending on how you implemented it. And I can just compare this new item with every item in the linked list. So searching takes linear time because in the worst case, I would have to go all the way. Maybe this is my largest item. But when I figure out that I want to insert it between these 2 elements, insertion is super fast. That's O1 with the links. So, but generally speaking, if you look at these 2 algorithms, their runtimes does not really change in terms of asymptotics based on whether you're using a linked list or an array, right? So let's just consider insertion sort, for example. In insertion sort, if I'm using an array, every time that I'm inserting a new item, sure, I can find its place really fast, but then in order to insert it, I have to shift everything to the right in the worst case. So every insertion is going to take linear time. It's going to take O(n) time. And then I'm inserting n elements or n minus 1 elements, so it will take n squared time overall, right? So that's if I use an array. And which, by the way, means that if I'm using an array, even though I can do a binary search to find the location really fast, it's not really worth it. I wouldn't do it, right? Because I'm paying the linear cost for every insertion anyway. Okay, but if I have this as a linked list, then what? Then searching and finding where I want to insert is the step that actually takes all of the time. So in the worst case, I would have to basically spend O(n) time doing the search. And after I'm done with the search, I can insert in O(1). But again, every insertion includes a search. So I'm spending O(n) time to add every new element. So my total runtime is O(n) squared. So that's for insertion sort. You can do the same kind of argument about selection sort. If I'm finding the minimum element every time, eventually this one off. Yeah, if I'm finding the minimum element every time, if it's an array, finding the minimum element, I have to go over all the elements. It takes linear time. But it's the same if it's a linked list. I have to go over all of the elements. So it's n squared with both linked lists and arrays. Okay. But now we actually have one other algorithm which is interesting to talk about, even though this one is also not going to give us a better runtime. And that's bubble sorts. Again, let me just shuffle these things, and it's not good to. Okay. It's not very random, but okay. So let's say these are my numbers. And let's say I want to sort this. And for some reason, I don't want to use a different array now. I just want to do it on this one array. And this can also be done with a linked list again. So here's what I'm going to do. I first take items at positions 0 and 1, and I compare them with each other. And if the order is not correct, I would just swap them. So whenever the order is not correct, we say that we have an inversion. For example, here I have 4, which is larger than 1, but has come before 1. That's called an inversion. So I just swap 4 and 1. Okay. And then I go to the next pair, 4 and 8. Again, I see that I have to swap. So, oops, no, I don't have to swap. 8 is already bigger. I'm bad at this. Okay. Then I go to 8 and 10. Again, I don't have to swap. This is fine. Then I look at 10 and 5, and I see that I have to swap. So I will swap them. And then I will have 10 and 6. And again, I have to swap. So I just... Okay. So this is my new order. And as you see, this is not necessarily sorted yet. But I can keep doing the same thing again. Now, the property that is interesting for me is that if I just start from the beginning and look at every pair of consecutive numbers, and if they're not in the right order, I swap them, I will always get my maximum element at the end, right? So that's the property that is interesting, because imagine this maximum element, it was somewhere at the beginning. So at some point, I would reach this maximum element, right? So let's say here. But then I would compare it and swap. And then I would compare it with the next one and swap, and so on. So my maximum element will be pushed to the end. So even though this doesn't sort the entire array in one go, it guarantees that my maximum element goes to the end. And when the maximum element is at the end, it will never move, right? It will remain there forever. So if I do this another time, the second maximum element will also go to the right place. Right, so I do this again, 1 and 4, I don't have to swap. 4 and 8, I don't have to swap. 8 and 5, I have to swap. So 5 goes here, it goes here. And then 8 and 6, again, I have to swap. And then I have 8 here. And as you see, the second highest element is now in the correct position. Now, in this case, I just got lucky and the whole thing is sorted. But in general, we can just make an inductive argument that if I do this I times, I am sure that the last I elements are correct. They are the largest I elements and they're in the correct order, right? So in general, I can do this swapping pass over my array or my linked list n times, and or technically n minus 1 times, and that guarantees that the whole thing will be sorted. Now, again, this algorithm has the same runtime as the previous ones asymptotically. It's a quadratic algorithm because every time that I'm going over the array, I'm spending On. I'm comparing index 0 with 1, 1 with 2, 2 with 3, so on. I'm doing n comparisons and sometimes swapping elements. So every time that I'm going over my array, I'm spending On time, but I have to do it n times. So it's n squared. So these are the 3 most famous quadratic runtime algorithms for sorting. Let me go back here now. Okay. And well, I will give you some slides that have the pseudocodes for this later, but let's just write the code. So let's just start with which one? Let's do selection sorts. Okay. I'm just going to, again, like before, I'm going to read some number n, and then I'm going to read an array of n numbers, and then I'm going to sort it and print it. So let's say my maximum n is 10 to the power of 7, and a little bit more. And let's say I have an array A, which is of size max. So, and here I just say for I from 0 to n, or n minus 1, read AI. And let's say I have another array B, which is going to be my solution. Now, in selection sort, every time I just want to find the minimum element, and I want to put it in the array B. So I say for I from 0 to n, now my goal is to find the minimum elements, minimum remaining elements, and put it in BI. Okay. So what do? I take the minimum value, whatever it is, or actually I can look at the minimum index. And let's say that I put it as -1 initially. And then I say for every j from 0 to n, if aj is less than a min index, or if I don't have a minimum yet, if min index is -1 or this, then my min index becomes j. And then I just say bi becomes b min index. Now, what's wrong with this? Can I just do this and then at the end just print my array B? Is this fine with the sorts? Let's see. Let's say I do compile it. And let's say I have 5 numbers. These are my 5 numbers. What's happening? So what's wrong in this code? Yeah, that's a typo, right? Actually, I was thinking of something even more important than that, but even this will not fix it. Now it's just printing the minimum element over and over again. So basically the problem is that when I'm finding the minimum element, I'm not really removing it from the list, right? So I have to make sure that I don't take the same minimum element again. Now you can have an array of Booleans to remember like what you put in and what you didn't put in, or you can just do something like this. When you put it here, you change the value at that minimum index to a huge value, right? So a value that is larger than everything you've seen. Let's say if I know all of my numbers are smaller than this, I can just put it. And actually in C++, you can do this, which is the largest value that fits in an integer, but ask your C++ instructors about that. 62578, and now it sorts it. Okay. But this is a terrible implementation, right? Why is it so terrible? Because I don't want to use this extra memory here. Can't I just do it in A itself? Well, I should be able to just do it in A itself, right? So instead of doing this, I can always say, when I'm here, I can say, let's keep the sorted part at the beginning of my array A, and let's keep the unsorted part after the sorted part, right? So when I'm here in my while loop, I want to say, assuming that A0 to AI minus 1 is already sorted, find the minimum element in AI to AN minus 1 and put it in AI, right? If I can do this, then I'm happy. And then I don't need a separate array. I can just use my array A. Again, I will put pseudocodes of all of these on canvas. So now, again, I have to just go for J, but J now starts at I, because I already know that everything until index I minus 1 is sorted. And I say if min index is minus 1, or I mean, whatever, I can just put my min index to be I initially so that I don't have to change it later. And then I can just say if AJ is less than a min index, the minimum index becomes J. And then all I have to do is that I have to make sure that the element that is at min index comes to place I. But I shouldn't overwrite the element that is currently at place I. So I can just swap them. So I can just write swap a min index and AI. Okay. 5, 6, 2, 5, 7, 8. Okay. Now, let's see how much time these things take. So I had an input generator from last session. Do I have it still? Yes. So I can just use this, and I'm going to call it IG. So let's generate an input with 10,000. And then let's run this and give it the input. And I don't care about the output, so I say just write the output to output at this. So that was pretty fast. You see, for 10,000 elements, it did it almost instantly. Now, let's do it for 10 to the power of 5. And again, let's time it. Now, as you see, this one is taking quite a while because our algorithm is quadratic. And like, 11 seconds. So that's how much time I need on my laptop to do 10 to the power of 10 times whatever constant there is operations. But I mean, fine. If I do 10 to the power of 6, it will take much more time, and we don't have enough time to wait for that, right? Okay, so this is selection sort. But now let's do the other one. I'm not going to do all three. Let's just do bubble sort. Okay, so I'm going to create bubble sort.cpp. Again, reading the input. And let's say I have some max n. And then, okay, so in bubble sort, the idea was that every time I just started from the beginning of my array, and I kept comparing. I kept saying, is AI greater than AI plus 1? And if it was, then I would just swap them. Swap AI and AI plus 1. Okay, but we said we should do this n times, or actually n minus 1 times. So let's just do this n minus 1 times, or n times, who cares? It's the same runtime anyway. And yeah, that's it. That's the whole thing. Literally 4 lines of code. And then I just print it. Okay. Now again, let's say 5. These are the 5 numbers. And what? No, so swap just works in C++. It's fine. You can implement it on your own, but yeah, it's in the library. Now, again, let's compare this with the previous one. So let's give it the same input that we gave to the previous algorithm. So the input size was 10 to the power of 5, 100,000 numbers. And it will probably take maybe a little bit less, I don't know. But it's a quadratic algorithm, so the difference is just a constant factor. Okay, this is actually taking more. Okay. But these are not the algorithms that are most interesting for us. These are actually the simplest sorting algorithms. And of course, they're the algorithms that take the most time. This one is taking much more time than I expected. Maybe something happened to my laptop. I don't know. Okay. I'm going to just stop it. But what we're interested in are faster sorting algorithms. And especially the main topic of this session is merge sort. And the idea of merge sort is very similar to the divide and conquer idea that we saw in the previous session. So let's say I have an array and I want to sort it. So I have this array of size n of numbers, and I want to sort it. I just cut it down the middle, and then I sort each of the halves recursively. So I just call my sort function recursively on the left part and then on the right part. Okay, what happens then? I basically get a sorted left part and a sorted right part. But now I have 2 different sorted arrays. I wanted to have just one, right? So I have to merge these 2 sorted arrays. So this is my pseudocode. So if I want to do merge sort on an array A, and let's say, again, I have a begin index and an end index. So I want to sort everything between the begin index and the end index. I just take my midpoint, which is going to be literally the midpoint, begin plus end over 2. And then I call my sorting algorithm recursively. So I first say sort the array A from begin to mid. And then I say sort the same array in the second half from mid plus 1 to end. And now that these 2 halves are sorted, I have to somehow merge them into one sorted array. Now, how can I do this? Well, again, I can do something similar to the selection sort, except that I do it in a more clever way. So in selection sort, we were always finding the minimum item and putting it at the beginning of the array. Okay. So if I know that L is sorted and R is also sorted, where can my minimum item be? It's either at the beginning of L or the beginning of R. So in order to find my minimum item, I just need one comparison. I just need to compare the beginning of L with the beginning of R. And whichever was smaller is my minimum item. So I compare this one with this one, and whichever was smaller, I put it as the first item. Let's say this one was smaller, so I put it here. And let's say, removed it from. So what does this mean? Again, I want to find my minimum item. So I just repeat the same thing. It's either the head of the left side or the head of the right side. And whichever is smaller is now my new minimum item. I put it as the second item, and so on. And I just continue this. And I do this until everything is sorted. So this operation is called merge. And the really important point here is the runtime analysis, but we will talk about that. So I would just do merge on A, and let's say I give it the begin, mid, and end. You don't need to give it the mid because you can compute it based on begin and end, but whatever, let's say I'm doing it. Now, how much time does my merge operation take? It's O(n), because every time I'm finding the minimum remaining item, and in order to find it, I'm just comparing two items. So I'm just doing one comparison. And of course, I do this n times until I sort the entire array. So my merge is always going to take O(n). Okay. Or to be more specific, it's going to take end minus begin plus 1. Right? Because that's my end. Right? So based on that, I can actually analyze the runtime of my merge sort. So let's say I have an array of size n, and I want to run the entire merge sort algorithm on it, right? And let's say T of n is the worst case execution time of merge sort on an array of size n. Okay. Now, what do I know? I know that when I want to sort an array of size n, well, again, we forgot the base case. The base case is that if my array size is 1, I don't do anything, it's sorted. Okay, so in my pseudocodes, I always forget the base case. But if you do this in the exam, we will not give you the marks. So you have to write the base cases. So my base case, basically, actually, let me write it here, is that if my end is less than or equal to my begin, which means that I have 0 or 1 elements, then just return, don't do anything, because it's already sorted. Okay. My time is going to be constant if n is 1, right? Otherwise, I'm cutting n down. So I'm cutting my array in 2 halves and then sorting the left half and then sorting the right half. So this would be 2t of n over 2, right? Because I'm sorting 2 arrays of size n over 2. And then after that, I'm doing the merge operation, which we said takes O(n). So plus O(n). Now, this is the exact same recurrence that we solved in the last session. And we actually saw that the answer to this is n log n, right? So now I know that my runtime, T of n, is in O of n log n. Okay? This is a huge improvement over the previous algorithms that we had, because the previous algorithms were taking order n squared. This is n log n. N log n is much faster. Now, let me show you an example, and then if we have time, let me code this. Okay. Let's see, this is going to be kind of part 6. Let me do with 8 because I want it to be a power of 2 so that I can do it more easily. So 8 cards. Hopefully this is the last time I'm doing this. Okay. So these are my 8 cards. Okay. You can see it, right? Okay. So these are my 8 cards. So the first thing I do is that I break them down into 2 sets of 4. And then I want to sort each set separately. So let's say I want to first sort this one, 8, 11, 4, and 1. Again, I break it down into 2 parts, and I sort each part separately. Now, I have this 8 and 11. I want to sort it. I break it down into 2 parts. Okay. Now I say that each part has size 1, so it's already sorted. So now I have to merge these 2 parts. I have to merge 8 and 11. So I look at 8 and I look at 11. I see that 8 is smaller. So in the merge, 8 comes first. And then I don't have anything here. I only have 11. So 11 is smaller than nothing. 11 comes next. I do the same thing here. I have 4 and 1. I separate them. I sort each of them separately, which is just doing nothing because it's size 1. And then I merge them. And when I want to merge here, I see that the 1 on the right is smaller than the 4 on the left. So I first put 1. Then I have the 4 on the left. I don't have anything on the right. So I put 4. Now I have to merge these 2 stacks, right? So in order to merge them, I have to first look at the head of each side and see which one is smaller, and 1 is smaller. So I'm going to take 1 and put it at the beginning of my sorted array. Now, again, I still have a left array, a right array, and a sorted array. I look into the head of the left array and the head of the right array. I see that the head of the right array is smaller. So I'm going to take this one and put it in the sorted array. Now, I look on the left-hand side, 8 and 11. I don't have anything on the right. Because I don't have anything on the right, I just take whatever I have in the left and put it here. And then again the same. So this sorted the first half. Now remember, we still have the second half. Okay, so I'm going to do the exact same thing on the second half. First divide it in 2 parts, then this part gets divided, then it gets merged, 5 and 10. Then this one gets divided, then it gets merged. When I merge, 3 comes before 6. And now I have to merge these 2. Again, I have a left side, a right side. I just compare the smallest element. The smallest element on my right side is smaller than my smallest element on the left side. So it comes here. Now I have 5 on the left, 6 on the right. So I take the 5. I have 6 on the right, 10 on the left. I take the 6. I don't have anything on the right. So I just take that. And finally, these are my 2 parts, which are each sorted. Oh, this is hard to show. Okay. So these 2 parts are sorted. I cannot show all of them together. One is, okay. And now I want to merge them. So again, I will just compare the smallest element on each side. And 1 is smaller than 3, so I take 1. Then 3 is smaller than 4, so I take 3. Then 4 is smaller than 5, so I take 4. Then 5 is smaller than 8, I take 5. 6 is also smaller than 8, I take 6. 8 is smaller than 10. 10 is smaller than 11. And finally, I only have 11 and nothing on the other side. And this is sorted. Okay. I hope this is the last time I do these kinds of examples in this course. Hopefully, the next algorithms will be so complicated I wouldn't be able to do an example. Okay. Coming back here. We have only 10 minutes. Let's actually try to code this. So we saw the pseudocode here. Let's do, this part is just reading the input. I copied it from the previous code. And then I'm going to say call merge sort on the array A from index 0 to index n. Actually, n minus 1, right? And this is my merge sort. I have an array. I have a begin index. I have an end index. And I say my middle point is just begin plus end over 2. And then I say first sort the left half. So do merge sort on A from begin to mid. Then sort the second half, do merge sort on A from mid plus 1 to end. and then finally merge them together. So merge on A, begin, mid, end. Okay, so I have to now write my merge function, which takes an array A, it takes the begin index. I could have avoided passing the mid, but I'm doing it anyway, and an end index. Now, I have to have basically 2 pointers. One that points to the smallest element on the left side, and one that points to the smallest element on the right side. So I will have a left pointer. Let's just call it L. And initially, it points at begin, at the first element. And then I have a right pointer, and initially it points at middle plus 1, which is the index, right? And let's say that I want to write my answer in B. So I will have, I don't know, a third pointer. I'm going to call it T. And initially it's just at 0. Now, here's the thing. Every time I have to do a comparison. And let me just create a loop. I will write the loop condition later. I'm going to do a comparison inside this loop. I want to compare the smallest element of the left side with the smallest element of the right side. So AL and AR. But the problem is that maybe 1 or 2 of these elements don't exist. Okay, so when would you actually put the element from the left? You would put it in if the element on the right exists and is bigger than the element on the left, or if there is nothing remaining on the right. So I say if there is nothing remaining on the right, which means that R is already past end, right? Or, okay, and I have to say if something is remaining on the left, which means that L is less than or equal to mid. Well, I don't need to actually do that, so I can just do this. I can say if the right-hand side has already ended, and or the right-hand side hasn't ended, but the left min element is smaller than the right mid element, then just copy the left mid element. So BT becomes AL. Okay. And I have to increase both T and L, and I'm really lazy. So I write it like this usually. Okay, this is bad. Don't do this. Okay. Otherwise, I have to take BT and make it into AR. I'm taking the element from the right side. Again, I'm a very bad person, so I'm doing this. Okay, for how long should I do this? I should do this as long as I have some element on the left or some element on the right. So I have an element on the left if L is less than or equal to mid. I have an element on the right if R is less than or equal to end. Okay, so if any of these things happens, then this is just saying I have to take the left element. This is saying I have to take the right element. Now I have to copy from B back to A. So for I from begin to end, AI becomes B I minus begin. Okay, I'm just copying it back here. Because I sorted and put the sorted things in B, I want to put it back in. And hopefully I don't have a bug. I don't know. I'm old these days. I have a lot of bugs. So 8, 1, 2, 3, 4, 5, 6, 7, 8 numbers. Yes, I have a bug, definitely. Oh yeah, the base case. We have to do the base case. Yes. So if end is less than or equal to begin, just return. I always forget the base case. Let's see. Yes, that was the problem apparently, but I also forgot to write the answer in the end. So for I from 1 to n, just write AI. Is work? Okay. Something is wrong. Okay, let's go back and see what's wrong.
I think the vowels and
No, while I have some element remaining. So while, oh, this should be L is less than mid or, right? No, that's fine. L less than or equal to mid or R less than or equal to end. If R is greater than n, this means the right side is done, or the left side is less than the right side. Then I put, oh, okay, yeah. I have to do it like this. I have to say L is less than or equal to mid and, right? So what are the cases where I would take something from the left-hand side? It's either the case where the right-hand side has run out, or both sides are there. So the right-hand side hasn't run out, the left-hand side hasn't run out either, and the left element is less than the right element. That's the only case where I would take something from the left. Okay. Let's see, does this work now? Yes. Okay. I'm sure you can implement this in simpler ways as well. And again, especially this part, I hate myself for doing this, but I've been doing this for 20 years at this point, so I cannot change it. Okay. One last interesting point is this idea of inversions that we talked about. So I said an inversion is basically a pair of items that are in the wrong order. Now, the problem I want you to think about is that I give you an array and I ask you how many inversions there are, right? So this is homework, not compulsory, but please do it. It's this idea. I have a problem where the input just gives you n numbers, A1 to AN, and the output asks you for the number of inversions. In other words, what is the number of pairs I and J such that I is smaller than J, but AI is larger than AJ? See if you can solve this with merge sort.